At roughly 2.5 times the distance from the Sun to the Earth, the temperature of the young solar nebula fell below a threshold. It crossed that line not with any sound or visible change, but with a quiet physical fact: water vapor, drifting outward through the disk of gas and dust that surrounded the infant sun, met cold enough to freeze. The vapor became crystals. The crystals were small, each one barely wider than a wavelength of light, and they drifted in the dark in vast numbers, catching almost no light, making almost no impression on the immensity of the disk around them. But they were there, and across the outer reaches of the disk, where the sun's warmth had already faded to something little more than a dim suggestion, the same process was at work with methane, with ammonia, with carbon monoxide, each compound finding its own cold threshold, each compound crystallizing, each crystal beginning the long, slow work of gathering with others. This was the frost line, the invisible boundary in the early solar nebula, beyond which ice could exist and persist, and everything that drifted beyond it became raw material for the belt of frozen worlds that would one day ring the outer solar system. The disk itself was enormous. It spread outward from the young sun across distances that require patience to hold in the mind. From the frost line, the disk continued outward for tens of billions of kilometers, thinning and cooling as it went, its outer reaches so distant from the sun that the light arriving there was already ancient by the time it crossed that space. In those outer reaches, the solid material was almost entirely ice, water ice first, then methane ice, then more exotic compounds that only solidified in the deepest cold. The gas was sparse and the solid particles were small, and between them lay vast distances of near nothing. But over time, time on a scale that makes almost any other kind of patience seem brief, the particles moved. They drifted toward each other under gravity. They collided gently, and when the collision was gentle enough, they stuck. Small clusters became larger ones. Larger clusters began to pull in their neighbors more strongly. The process was slow and irregular, full of collisions that destroyed, as well as collisions that built, but the direction of it was always toward larger bodies, toward things with enough gravity to hold themselves in a rough sphere, toward the first generation of planetesimals, icy, dark, cold, drifting objects a few kilometers across, the ancestors of everything now found in the Kuiper Belt. 4 billion years is the scale of time across which all of this happened. Not 4 billion years of dramatic event, but 4 billion years of slow change, of accumulation and collision and drift, of orbital paths gradually settling into the shapes they hold today. A human lifetime placed against that span is so brief that the comparison barely registers. Even the whole of recorded human history, all of it stacked together, amounts to a thread too thin to see against that background. The outer solar system built itself on geological patience of a kind that the inner planets, with their active geology and shifting climates, have mostly overwritten. But in the cold beyond Neptune, where temperatures hover close to absolute zero, and the chemical processes that break things down are glacially slow, much of what formed in those first hundreds of millions of years has simply persisted. The ice is still ice. The orbits are still close to the shapes they were nudged into long ago. The Kuiper Belt is not a ruin of the early solar system. It is a remnant, which is a different thing, something that endured rather than something that was broken. The band of space it occupies runs from roughly 30 times Earth's distance from the Sun out to approximately 50 times that distance. These numbers are large enough to feel abstract, but there is a comparison that makes their size felt more directly. Light travels at the fastest speed anything in the known universe can move, A beam of light crosses the distance from the Sun to the Earth in just over 8 minutes. To cross the full width of the Kuiper Belt, from its inner edge to its outer edge, that same beam of light needs more than 3 hours. The belt is not a narrow ring. It is a vast torus of space, a thick annular band so wide that even the fastest thing in the universe takes most of a working day to traverse it. Within that band, the objects are sparse enough that an observer placed anywhere within it would see mostly empty space in every direction. The distances between individual objects are enormous. The belt is full in the sense that it contains hundreds of thousands of bodies larger than 100 kilometers across. But that fullness is a statistical fullness, a population distributed across a volume so large that individual members are almost never close to one another. The bodies within the belt are not arranged randomly. They follow patterns. The patterns are the product of forces that operated long ago, and reading them now is something like reading a record pressed into stone. The forces are gone, but their signature remains. The most important of those forces was Neptune. Neptune formed, as the other giant planets did, in the inner part of the outer solar system, somewhere far closer to the Sun than its current position. In the early solar system, the giant planets were arranged more compactly, their orbits closer together, their gravitational interactions more intense. The disk of planetesimals that surrounded them contained far more material than survives in the Kuiper Belt today. And over a time scale of perhaps tens of millions of years, the giant planets migrated. Jupiter moved inward. Saturn, Uranus, and Neptune moved outward. Neptune's outward migration was the most consequential for the belt, because Neptune traveled through the outer disk, not across empty space, but through the very population of icy bodies that had accumulated there. As it moved, it scattered them. It flung some inward. It sent others onto highly elongated orbits. It captured others into special gravitational relationships with itself, locking them into patterns of orbital repetition that are still visible today. And when it finally settled into its current orbit, roughly 30 AU from the Sun, the belt that remained behind it was a sculpted thing, sorted and sifted by the passage of a world 4 times larger than the Earth. The sculpting Neptune left behind is visible now in the way the belt's population is divided. On one side of that division are the cold classical KBOs. The name is a technical one, but the physical picture it describes is simple. These are objects that formed roughly where they orbit now, that were never pulled strongly inward or flung into tilted paths, that have been following nearly circular orbits close to the plane of the solar system for most of 4 billion years. Their orbital inclinations, the angle at which their orbits tilt relative to the flat disk of the solar system, are typically less than 5 degrees. That is a very small tilt. Earth's orbit is itself tilted about 0 degrees, since it defines the reference plane, and most of the inner planets orbit within a few degrees of that plane. The cold classical KBOs orbit in the same style, close and flat and steady, undisturbed. Their paths today resemble almost exactly the paths they had when they first assembled from the disk. No great force has moved them significantly. They have simply continued, orbiting in the quiet, cold dark, carrying within their composition and structure information about what the outer solar nebula was made of at the time of planet formation, information that no other part of the solar system has preserved so cleanly. The hot classical population is a different matter. The word hot here has nothing to do with temperature. These objects are just as cold as their counterparts, all of them far below the freezing point of water. Their surfaces coated in ices and organic material. In orbital mechanics, hot means stirred, perturbed, scattered away from the calm. The hot classical KBOs carry orbital inclinations that can be 10, 20, 30 degrees or more, and their orbits are often more elongated, more eccentric, more tilted. These characteristics are consistent with objects that were pushed. Neptune's outward migration carried gravitational disturbances ahead of it, like a wave, stirring the population of icy bodies it encountered, lifting some into tilted paths, compressing others' orbits, shuffling the outer disk, the way a slow hand might stir a still surface into long rolling motion. The hot classical objects are those that felt that stirring most directly. Many of them likely formed closer to the sun, in regions of the disk where the solid material was denser, where accretion proceeded faster, and where larger bodies could grow. And then, when Neptune's influence swept through, they were scattered outward to the orbital positions they occupy today. They are not native to the region where they now reside. They are a transplanted population, and their tilted, eccentric orbits are the record of the journey that brought them there. Between the cold and hot classical populations and interpenetrating with them are objects locked into what are called mean motion resonances with Neptune. A resonance in orbital mechanics is a relationship between two orbiting bodies in which their orbital periods form a simple ratio, 2 to 1, 3 to 2, 4 to 3, and so on. This means the two bodies return to the same relative configuration repeatedly, at regular intervals, and if the ratio is a simple one, the gravitational nudges they exchange at each of these encounters add up coherently over time rather than canceling each other out. The result is a kind of gravitational stability. Objects in resonance are not simply pulled this way and that at random, but instead experience repeating patterns of force that, in the right configuration, keep them on stable orbits rather than ejecting them from the belt entirely. The most populated of these resonances lies at roughly 39.5 AU from the Sun, where objects complete 2 orbits for every 3 that Neptune completes. The period of one of these objects is approximately 250 years. For every 2 such orbits, Neptune completes 3, and the two bodies return to the same configuration, the same alignment of their positions, and the same direction of gravitational pull. Objects at this resonance are called Plutonos, after their most famous member. There are hundreds of them, perhaps thousands. They trace elongated orbits that periodically bring them close to Neptune's path. Yet the resonance ensures that when they are at their closest to Neptune's orbit, Neptune itself is far away on the other side of the Sun. The arrangement is precise and persistent, a gravitational dance choreographed long ago by the dynamics of Neptune's migration, still playing out on the same pattern, orbit after orbit after orbit. Farther out, at roughly 47 8/10 AU, another resonance operates on a 2 to 1 ratio. Objects here complete 1 full orbit for every 2 that Neptune completes, and the alignment repeats on that same schedule. This resonance marks something important. It sits close to the outer edge of the classical Kuiper Belt, the boundary beyond which the belt's population drops away sharply. The outer edge of the classical belt is not a gradual fade, but a step, a pronounced cliff in the number of objects as a function of distance from the Sun. At roughly 48 AU, the belt simply ends, or nearly so. Beyond that distance, the population is sparse and scattered, dominated by objects on highly elongated orbits, rather than the nearly circular paths of the classical belt. The sharpness of this edge is not a coincidence. It marks the outer limit of Neptune's gravitational reach during its migration, the farthest distance at which Neptune's outward sweep was able to clear, sort, and sculpt the primordial disk. Beyond it, the solar nebula's original population largely survives in its scattered or depleted form. Within it, Neptune's influence has organized everything into the structured distribution visible today. That edge, that sharp drop in orbital space, is itself a kind of fossil. It was carved into the belt's population during the first tens of millions of years of solar system history, and it has been preserved ever since by the same forces that created it, the ongoing gravitational influence of Neptune, which continues to define the dynamical boundary of the classical belt, even as individual objects slowly drift in or out of stability across millions of years. To encounter that edge observationally, to track the population of objects as a function of distance, and find it dropping abruptly at approximately 48 AU, is to find the imprint of Neptune's ancient migration preserved in the current architecture of the outer solar system. The force is long past. The signature of it endures. Beyond the frost line, in the cold outer reaches of a disk still settling into itself, the crystals of water ice drifted in their millions. That image bears staying with the moment, because it is the beginning of everything that would become the Kuiper Belt. Not a dramatic beginning, not a spectacular one, but a patient one. The crystals were small, the distances between them were vast. The time available for them to gather was enormous, and the gathering happened, slowly, in the cold and dark, far from the warmth that was already shaping the inner planets into the rocky, geologically active worlds they would become. Out here, there was no volcanic eruption, no continental collision, no ocean or atmosphere to complicate the accumulation. There were only the crystals, and gravity and time. And from those three ingredients, over the span of the early solar system's first 100 million years, the first generation of icy planetesimals built themselves. The disk from which they formed was not uniform. It had structure, density waves, chemical gradients, regions where the solid material was more concentrated, and regions where it was thin. The frost line marked the most important of these boundaries, the one that divided the rocky inner disk from the icy outer one. At the frost line itself, the solid surface density of the disk increased sharply, because all the water that had been in vapor form inside the line became solid just outside it, adding its mass to the available building material. The region just beyond the frost line was in this sense an especially rich environment for the assembly of planetesimals. Bodies formed there quickly, in astronomical terms, growing through successive collisions and gravitational accretion into objects tens of kilometers across within the first few million years of the solar system's existence. These were not yet planets. They were not yet planet-sized. But they were real, solid, three-dimensional bodies, dark and cold and icy, orbiting the young sun in the same flat disk that would one day become the plane of the solar system. As Neptune's gravity swept through this population, it did not simply scatter objects uniformly. It sifted them, and the sifting was systematic. Objects whose orbital periods happened to be near a simple resonant ratio with Neptune's period felt the planet's gravitational pull in a coherent reinforcing pattern with each return of the alignment. Some of these objects were pulled into orbits that strengthened the resonance, making them more stable there. Others were pushed to the edge of stability, from which they would eventually drift into more scattered configurations over millions of years. The process was slow and selective, and its result was the population of resonant objects visible in the belt today, each one in its resonance, because the dynamics of Neptune's migration placed it there, because it happened to be in the right place when the resonance swept through during Neptune's outward passage, and because the gravitational pattern that captured it has held it in that pattern ever since. The three. 2 resonance, with its hundreds of captured objects at 39.5 AU, is the strongest and most densely populated of these resonant groups. The objects there move in elongated orbits, diving inward toward and sometimes past Neptune's orbital distance, and swinging back outward before Neptune can approach them closely. Over the course of a single orbit, which takes on average about 250 years, each of these objects traces a long oval path around the Sun, repeating the same gravitational alignment with Neptune every 2 of its own orbits, every 3 of Neptune's. That alignment has been repeating since the early solar system. It has repeated millions of times, and it will continue to repeat for millions of years to come, as steady and as patient as anything the solar system contains. The orbital resonances are not the only pattern. The cold classical belt, flat and circular and undisturbed, also shows patterning of a different kind. Its outer edge at 48 AU is sharp and clear. Its inner boundary, where it merges with the populations at and beyond the 3-2 resonance, is softer and more complex. Within the classical belt span from 42 to 48 AU, the population is not uniform. There are regions of higher density and lower density, corresponding to the locations of weaker resonances, regions of stability, and regions of relative depletion. The belt is not a smooth ring, but a structured distribution, a set of populations organized by orbital dynamics, each with its own origin story, its own relationship to Neptune, its own place in the sequence of events that built the outer solar system over its first hundreds of millions of years. The outer edge of the classical belt holds its shape across time, not because nothing disturbs it, but because the forces that would disturb it are themselves periodic and bounded. Neptune's gravitational influence reaches outward, but it reaches with diminishing strength, and beyond a certain distance, its ability to move objects significantly drops below the level needed to reshape the belt's boundary. The cliff at 48 AU is where Neptune's reach runs out. It ran out there during the migration, when the planet settled into its current orbit and the sifting process came to an end. It runs out there still, and the edge carved by an ancient dynamical event has been held by the ongoing quieter operation of the same force ever since, preserved the way a form in cold stone is preserved, not actively maintained, but simply too stable to erode. Within the belt, the cold classical objects move through the dark in their nearly circular paths, close to the plane of the solar system, undisturbed by the close gravitational approaches that shape the hot classical population and the resonant objects. They have been in their current orbits, or very close to them, for most of the 4.5 billion years the solar system has existed. They formed where they are, from the local material of the disk, and the only significant gravitational influence on their orbits since formation has been the slow, gentle influence of Neptune's mean motion resonances, which have slightly adjusted the boundaries of the classical belt without dramatically changing the paths of the cold objects within it. Their orbits today are close to pristine. They are as close to a direct record of the conditions in the outer solar nebula as anything in the solar system offers. The Sun, seen from within the Kuiper Belt, is still the brightest object in the sky, but it is a small and cold-looking brightness, a point of light more intense than any star, but reduced from the disk of warmth that illuminates the inner planets to something that would look, to a human eye, like a very bright star rather than a sun. At 40 AU from the Sun, the light arriving from it is 1,600 times dimmer than the light arriving at Earth. The warmth is correspondingly reduced. The surface temperatures of KBOs at that distance are typically somewhere between 30 and 50 degrees above absolute zero. temperatures so low that most gases freeze, that even the nitrogen that makes up most of Earth's atmosphere solidifies, that chemical reactions capable of breaking down complex molecules proceed at nearly imperceptible rates. It is in this cold that the belt's chemistry has been preserved. It is in this cold that the surfaces of KBOs have remained close to the composition they had when they first formed, altered only by the slow action of cosmic rays and ultraviolet radiation on their outer layers, not by the heat or chemistry that drives geological change on the inner planets. The resonances, then, are the signatures. They are the marks left in the orbital architecture of the Kuiper Belt by the forces that shaped it long ago. They tell a story not through words, but through the distribution of objects in space, through the clumping of populations at certain distances, the sharp depletion at others, the tilt and eccentricity that distinguish the hot classical objects from the cold ones. Reading that story requires patience, both in the original data collection, the slow accumulation of orbital measurements for hundreds of individual KBOs, and in the modeling that translates those measurements into a picture of the early solar system. But the story is there. Neptune's passage through the primordial disk left a record, and the record is written in the positions of objects that are still, 4 billion years later, following the paths that passage shaped for them. The tick of a cosmic clock is a useful image for the resonances, though it risks making them sound mechanical in a way they are not. They are not perfectly regular in the way a clock is regular. Individual objects within a resonance drift slightly in and out of its capture zone over time, and over very long periods, the resonance itself can fail to hold a particular object, releasing it into a different orbital state. The belt is not static. It loses objects slowly as resonant objects drift out of stability and fall inward into the scattered disk, or are eventually perturbed far enough to become comets. It has been losing objects since Neptune's migration ended, and the current belt is a reduced version of what it was, even in the early solar system, before the planet's passage scattered the bulk of its original population. But on the timescale of a human life, or of human civilization, or even of the few thousand years across which any human knowledge persists, the resonances are as stable as anything in the natural world. They repeat, they persist, and in their repetition they preserve, in the form of an orbital pattern still active today, the memory of the forces that created them, a memory written not in stone, but in the geometry of motion, not a record of the past in the conventional sense, not a fossil or a sediment layer or a chemical trace, but something more abstract and perhaps more durable than any of those, a gravitational pattern, a set of orbits, a repeating alignment of positions that has persisted for 4 billion years and will persist for billions more, long after every human civilization has come and gone, long after the planet that initiated the pattern has itself changed in ways we cannot predict. The resonances are not aware of what they are preserving. They have no memory in any ordinary sense. But the pattern is there, as real and as legible as anything the solar system contains, and the patient work of reading it, of measuring the orbital periods, the inclinations, the eccentricities of hundreds of individual KBOs, is the work of recovering a record of the early solar system from the structure of the one it became. The forces that built the Kuiper Belt are billions of years gone. The belt they built remains, cold and vast, and ordered in the dark, turning slowly around a distant star on orbits that still carry, encoded in their shapes, the signature of the ancient tide that gave them form. In wavelengths of light the eye cannot see, a faint signal travels from the surface of a small dark body at the edge of the solar system, crosses billions of kilometers of empty space, and arrives at a detector on the ground as a pair of narrow dips in an otherwise smooth curve. Each dip marks the same thing: water ice, frozen so hard and cold it barely sublimes, even over geological time, absorbs light at very specific wavelengths, near 1.5 micrometers, and again near 2 micrometers, and the absorbed light leaves its signature the way a fingerprint leaves its shape on a surface. The signal is quiet, the body is small and far, but the fingerprint is unmistakable, and it says that on this dark surface, even at the outermost edge of the solar system, the most familiar substance in the natural world is present: solid, ancient, patient, water. Water ice is the most abundant solid in the Kuiper Belt. It is not always visible to the eye because many surfaces have been chemically transformed by billions of years of radiation, and the pristine ice lies buried beneath layers of darker material. But the spectroscopic fingerprint, those precise dips in the infrared, rises from the surface regardless. Instrument after instrument, body after body, the same absorption features appear with a regularity that makes the ice feel almost inevitable, as though the outer solar system, this cold and distant province, simply is made of frozen water and always was, from the earliest hours of its formation. The ice did not travel there, it condensed there, in the dark and cold of the early solar nebula, out of vapor that had nowhere else to go. What sits on top of that ice is stranger, and in some ways more telling. Across the surfaces of many Kuiper Belt objects, the outermost layer is not clean white or pale blue, but a dark reddish brown, the color of rust or dried clay, or old wood left too long in weather. The color comes not from mineral iron, but from something organic, the slow product of ultraviolet light and energetic particles striking the simple ices, methane and nitrogen, and driving them through chemical reactions that build complexity over millions and then billions of years. Simple molecules bond and rebond and grow heavy and complicated, assembling into long-chain organic structures that no living thing made, that require no warmth or biology, that need only time and radiation and the raw materials of the outer solar system. These compounds are called tholins, a name coined in the 1970s by Carl Sagan and his colleague Bishun Kar, who first synthesized them in a laboratory by irradiating simple gas mixtures, and watched as the pale gas slowly darkened into a reddish-brown residue. The word itself comes from the ancient Greek for muddy, and the color it describes is one of the most common colors in the outer solar system, written across surfaces that have had the longest and most uninterrupted exposure to space. Tholins accumulate slowly. They do not form overnight. The reddest surfaces in the Kuiper Belt are the ones that have been unbroken, unrefreshed, unscraped by collision or geological activity for the greatest spans of time, surfaces that have simply sat, open to the sky, for hundreds of millions or billions of years, while the radiation did its quiet chemical work. A fresh surface, newly exposed by a collision, would start pale, the ice beneath unaltered and bright, and only gradually redden as the irradiation accumulated. The degree of redness, then, is in some sense a clock, though an imprecise one, reading out the duration of exposure. Across the cold classical Kuiper Belt, the redder objects tend to cluster in the same orbital families, the same gentle, nearly circular paths, as though they have shared not just a location, but a history of stillness, a common biography of undisturbed time. The colors of Kuiper Belt objects range across a wide spectrum, from neutral, slightly gray bodies that look almost like dirty snowballs, to the deepest, most saturated reds in the solar system. The population spans a gradient that no other region of the solar system matches in its width. Some bodies reflect light in shades close to carbon dark, absorbing almost everything the distant sun sends their way. Others are tinged with the pale pinkish hue of partially irradiated ice, and some are so deeply reddened that their surfaces absorb most incoming light and convert it to a dark, muted crimson that persists across the surface with a remarkable consistency, as though the irradiation has had time to reach equilibrium to color everything equally down to a certain depth. Each shade is a record. Each gradient encodes how long a surface has lived undisturbed, how much volatile ice it has held onto, how many high-energy particles have worked their slow chemistry in the dark. The surface colors of these worlds are not decoration. They are a language, and the alphabet is time. Beneath those ancient colored surfaces, the bodies themselves vary in ways that no visual examination could reveal. Size matters enormously in the outer solar system because size controls interior pressure, interior heat, and whether a body can organize itself into distinct layers. The smallest Kuiper Belt objects, those measuring tens of kilometers across, are thought to be rubble piles in the most literal sense, not solid rock, not even consolidated material, but loose aggregates of fragments held together by the gentle pull of their own gravity. They formed from collisions and accretion, gathered into rough heaps, and have remained that way, their interiors porous, their densities low, sometimes as low as half the density of water. If they contain water ice, and many do, the ice is not compressed into solid form, but sits loosely packed among the gaps, contributing very little structural integrity. These small bodies drift in silence at densities so low that were they placed in a large enough ocean, the smallest would float. The larger Kuiper Belt objects behave differently. Mass enough material into one body, and its own gravity begins to do work. Heat generates from the decay of radioactive isotopes trapped in the rocky component, short-lived isotopes that were abundant in the earliest solar system and burned through their half-lives in the first millions of years. In a large enough body, that heat was enough to soften and flow the interior material, allowing the denser rock and metal to sink toward the center and the lighter ices to rise toward the surface. This process is called differentiation, and it produces an internal architecture of distinct layers, a rocky core, dense and compressed, surrounded by an icy mantle that gradually grades toward the surface. The largest Kuiper Belt objects, the ones that stretch beyond 1,000 kilometers in diameter, likely underwent this sorting, their densities reflected. Uris, one of the largest known bodies in the belt, has a bulk density of roughly 2.5 grams per cubic centimeter, a value that sits far above water ice and points to a substantial interior proportion of rock and compressed material. That density tells its own kind of story, even from a distance, even without a single spacecraft having made a close approach. Between the rubble piles and the differentiated worlds lies a continuous range. Some mid-sized bodies may have partially differentiated, their interiors partly sorted, but not fully organized. Some may have been disrupted by large impacts and reassembled, mixing the layered material back into a rougher homogeneity. The population is not a simple two-category system. It is a spectrum of outcomes determined by initial size, initial composition, thermal history, and the violence or gentleness of subsequent collisions. Each body in the belt carries the record of these variables, encoded in its density, its shape, and the spectrum of light its surface returns. Among the cold classical Kuiper Belt objects, somewhere between 10 and 30% of all bodies do not travel alone. They move in pairs, two objects bound to each other by gravity, orbiting a shared center of mass at wide and gentle separations, each the companion of the other across the cold and empty space between them. These binary systems are not like the Earth-Moon system, where one body greatly outmasses the other, and the smaller body orbits deep within the gravitational dominance of the larger. In the cold classical population, the two components of a binary pair are often strikingly similar to each other. Similar in size, similar in brightness, similar in color, similar enough, in some cases, that they appear to have formed from the same cloud of local material, at the same time, in the same place, rather than one having captured the other in a later encounter. The configurations suggest common ancestry, siblings assembled from the same debris, rather than strangers drawn together by chance. The fraction of binaries in the cold classical population is far higher than elsewhere in the Kuiper Belt. The hot classical population, with its stirred orbits and higher inclinations and eccentricities, carries far fewer binaries per 100 objects. The scattered disk, the region of bodies flung to eccentric and inclined paths by close encounters with Neptune, shows fewer still. This pattern points to a fragility in the binary configuration. A close gravitational encounter with a large body, or even with a moderately sized interloper, can disrupt a widely separated binary, unpairing the two components and sending them off on separate paths. In the cold classical belt, where the orbits are gentle and the population density is lower, and the dynamical history has been quieter, those encounters have been rare enough that binaries formed long ago have been able to persist, essentially unchanged, for the full span of solar system history. How binary pairs form has been a question the orbital architecture of the cold classical belt has helped to answer. The leading picture, supported by computer models and reinforced by the properties of observed binaries, is one of gravitational collapse within a locally dense cloud of small particles. Where pebble-sized debris gathered in sufficient concentration, the local self-gravity of the cloud became strong enough to pull material inward all at once, and the collapse produced not a single central body, but a pair, or occasionally more, born together from the same region of the disk. This mechanism is called the streaming instability, and it leaves a very specific signature: binary components that are matched in size and color, orbiting each other at separations comparable to the size of the original collapse region, with very little relative velocity between them. The cold classical binaries fit that signature well. They are in this sense fossils of the formation process itself, physical proof of a mechanism that operated across the outer solar system in the first few million years after the sun ignited. A pair of similarly colored, similarly sized objects circling each other at a slow and wide separation, with no other body nearby and no sunlight bright enough to cast a clear shadow. The image is one of great patience. These binary systems have been moving together, tracing their mutual orbits, since before the Earth had any ocean on its surface, since before there were continents to drift. The space between the two components is not empty exactly, but it is very nearly empty, and nothing within it connects the two bodies except the invisible geometry of their shared gravity, a curve in space that pulls each of them always gently toward the other, and has been doing so for 4 billion years. The sheer number of Kuiper Belt objects is itself a subject worth pausing over. There are estimated to be hundreds of thousands of bodies larger than 100 kilometers across in the classical belt alone. That number is large enough to seem almost impossible, given how rarely any of them are visible without large telescope apertures, and it gives the belt the character of a genuinely vast population, a distributed collection of worlds, rather than a handful of anomalies. Yet for all that number, the total mass of the Kuiper Belt is surprisingly, even strikingly small. Add up every object in the belt, from the largest dwarf planets down to the smallest detectable bodies, and the combined mass amounts to something between 100th and 1/10 of the Earth's mass. This is not much. It is, in fact, far less than models of the early solar system suggest should be there if all those bodies had formed in place without subsequent loss. Formation models need more mass. The calculations that describe how kilometer-sized objects grow into 100-kilometer bodies through accretion and gravitational collapse require a certain density of material in the surrounding disk, and the density implied by today's Kuiper Belt is too thin by a large factor. Working backward from the current population, models suggest the early outer disk may have held somewhere between 10 and 100 times the mass currently present, and that most of it is simply gone, not destroyed, or not most of it, but scattered. Kicked out of the belt by the gravitational disturbances of Neptune's migration through the early disk, flung inward to become the bombardment recorded in the craters of the moon, or thrown outward to the farthest reaches of the solar system, far beyond the classical belt's outer edge. Some fraction became comets, some fraction escaped the sun's gravity entirely and drifted out into interstellar space. The mass that remains is a remnant, and recognizing it as such changes how the belt is understood. It is not a place where material has sat undisturbed since the beginning of the solar system. Most of it was disturbed, massively, during the period when the outer planets were rearranging themselves. What survives is what managed to find stable ground, the cold classical objects in their low inclination orbits, the resonant populations locked safely into step with Neptune's rhythm, the scattered disk objects far enough or eccentric enough to escape the worst of the disruption. The Kuiper Belt's current population is a selection, the portion of the early outer solar system's mass that threaded through a period of upheaval and came out intact on the other side. That selection has a shape, and the shape is informative. The distribution of object sizes in the belt follows a pattern, a smooth mathematical relationship between how many objects exist at each size, but the pattern has a kink in it. Above a certain size, roughly 100 kilometers, the number of objects per size class decreases more steeply than it does below that size. This break in the distribution has been interpreted as the signature of two different regimes. Smaller objects may have been produced primarily by collisions, the grinding and fragmenting of larger bodies over billions of years. Larger objects, the ones above the break, may be survivors from the original formation process, bodies big enough to have remained largely intact through the collisions that shattered their smaller neighbors. The size distribution, like so many other properties of the belt, is not random. It is structured by history, shaped by the specific sequence of processes that operated in the outer solar system over the full span of its existence. On the surface of a cold classical Kuiper Belt object, the environment is one of almost total stillness. The sun, at 40 to 48 astronomical units of distance, puts out roughly 1/500th the intensity of light it delivers at Earth. It is still the brightest object in the sky by an enormous margin, far brighter than any star, but it is cold light, insufficient to warm the surface above, around 230 degrees below 0 Celsius. At those temperatures, nitrogen and methane ices, where present, sublimate only very slowly. Volatile material that evaporated from warmer surfaces billions of years ago simply stays, locked in place by cold, so deep it functions almost like geological stasis. The surface does not change quickly. The chemistry is slow. The only active process is the quiet accumulation of further irradiation, building the Thalin layer molecule by molecule, darkening and reddening the surface 1 year at a time. Occasional impacts break the stillness. A small body, perhaps a fragment ejected from an earlier collision elsewhere in the belt, crosses the orbit of a larger body and strikes it. At the low relative velocities typical of the cold classical population, these impacts may not be entirely shattering. They can leave craters without destroying the body, or, at the smallest scales, they can add small amounts of material rather than remove it. A fresh crater exposes bright ice beneath the irradiated surface layer, a pale scar on a dark landscape, and over subsequent millions of years, that fresh surface slowly reddens again as the radiation catches up. The scar heals as much as anything at this temperature can be said to heal, and the surface returns to its uniform dark hue. The largest of the Kuiper Belt's worlds carry an additional complexity. Their surfaces, though cold, may conceal interiors that have not been entirely frozen and static since the beginning. The decay of radioactive isotopes, concentrated in the rocky core, generates heat that can persist in a large body for extended periods. Whether that internal warmth has ever been sufficient to drive geological activity at the surface of any particular body is a question that direct observation of those surfaces is beginning to answer. But even at a distance, the densities and sizes of the largest bodies imply interiors that are not simply frozen solid from core to crust. There is structure within them. There is history. The layering that differentiation produced has persisted, even as the surface has grown cold and dark and coated in organic residue, because the interior temperatures required to have created the layering in the first place were never so extreme that they have had to sustain themselves. They only needed to occur once, early, and the result has been preserved by the cold that followed. The surfaces of the largest Kuiper Belt objects also show a wider range of compositions than the smaller classical population. At sufficient size, a body can retain volatile ices that a smaller body would lose, because its gravity is strong enough to hold an extremely thin, very low pressure atmosphere, and the atmospheric presence slows the escape of sublimating molecules. Methane, nitrogen, and carbon monoxide ices, which would be lost from smaller bodies over geological timescales, can be found on the largest KBO surfaces because those worlds are, in some sense, barely big enough to keep them. The volatile ices are present as thin coatings, constantly sublimating on the sunlit side and recondensing on the cold side, cycling slowly around the body in patterns driven by the asymmetries of its illumination and its orbital path. The larger the world, the richer its surface chemistry can be, and the closer it approaches, in its own minimal way, to the atmospheric and geological complexity that only the largest and most geologically active bodies in the solar system fully express. The cold classical binary pairs carry a particular tenderness in the mind's eye. Two bodies, formed from the same cloud, held in each other's gentle gravity for the full age of the solar system, sharing the same dark orbit at 44 or 45 astronomical units from the sun, their surfaces reddened to the same color by the same unbroken span of radiation, too slow moving in relation to each other for either one to escape, too gentle in their formation to have shattered on first contact. They did not seek each other out. They formed already together and have simply remained so through everything the solar system has done around them. Their bond is not dramatic. It is the quietest possible relationship, maintained by nothing more than gravity and time and the absence of anything violent enough to break it. In the cold and the dark, at the solar system's unhurried edge, the binary pairs are perhaps the most undisturbed remnants of the conditions that made the solar system itself, two pieces of the same original cloud, still in each other's company after 4 billion years. The mass the belt has lost weighs on any accounting of the solar system's outer provinces, because if the current belt is a remnant, what was the original? What filled the space from 30 to 50 astronomical units before Neptune migrated, before the gravitational architecture was established, before most of the mass was scattered away? The models suggest a disk dense with material, with perhaps dozens of bodies the size of Pluto or larger, with a total mass that could account for the cratering record of the inner solar system's early bombardment. That original disk was the feedstock from which the ice giants themselves were built, the reservoir from which Neptune and Uranus gathered the last of their mass before the disk was thinned by the clearing processes their own gravity drove. The belt we observe today is the residue of that clearing, the fraction that threaded through the gravitational maze and arrived at stable orbits, and it is a small fraction of the whole. The objects that fill the cold classical belt carry their own kind of gravity beyond the physical. They are the most chemically pristine solid objects in the solar system accessible to observation. They formed early in the outer disk from the most primitive materials available, the water, methane, nitrogen, and rocky silicates that condensed from the solar nebula before any heat from the young sun had processed them into something different. They were never close enough to the sun for their interiors to be fully heated. They were never disrupted by the close planetary encounters that scrambled the compositions of the hot classical population. They have sat, essentially in place, since the first few millions of years of solar system history, slowly accumulating the irradiation record on their surfaces, while preserving the pristine chemistry of their interiors. Each one is a sealed envelope, its outer surface transformed by time and radiation, its interior still carrying the original composition of the outer solar nebula, largely unchanged. The reddish surface coloration that covers so many cold classical Kuiper Belt objects is both a veil and a record. It conceals what lies beneath it, the original ice, the original mineralogy, the original chemistry of the outer disk. But the veil is itself made of material derived from those originals, transformed by the same radiation that darkened it. The tholins are not alien to the ice beneath them. They are made of it. Ultraviolet photons struck methane molecules on the surface, broke them apart, and drove the fragments into new configurations, building complexity from simplicity without any blueprint and without any warmth. Over geological timescales, this process converted a fraction of the surface ice into a thick organic residue, and that residue has accumulated until it constitutes the dominant visual character of the surface. Looking at the reddish surface of a cold classical KBO, one is looking at a thin layer of transformed solar nebula chemistry, chemistry that took 4 billion years of patient irradiation to produce, laid over a substrate that has barely changed since the solar system was new. When the total accounting is made, the sizes, the densities, the binary fractions, the color gradients, the surface compositions, the population statistics, what emerges is a picture of the Kuiper Belt as a place of enormous variety packed into a relatively thin band of the solar system. It is not a uniform field. It is not a simple ring of undifferentiated debris. It is a layered, structured, differentiated population in which the orbital history of each object's class is written into its physical properties, and in which the physical properties of each object encode the specific conditions of its formation and subsequent history. The cold classical objects are red and binary rich and pristine. The hot classical objects are more varied in color and far more rarely binary, their orbital memories scrambled by early gravitational disturbance. The largest bodies have rocky cores and volatile ice surfaces and the beginnings of atmospheric chemistry. The smallest are loose collections of fragments, barely held together, dark and slow and solitary. All of them are real. All of them are present. All of them are orbiting the sun at distances so great that the sun itself shrinks to a bright point, and the familiar warmth of the inner solar system is something that has never reached them. There are hundreds of thousands of these bodies, larger than 100 kilometers across, perhaps billions of smaller ones, and all of them, the large and the small, the red and the gray, the binary pairs and the solitary travelers, the rubble piles and the differentiated worlds, all of them together sum to less than 1/10 of the mass of the Earth. What is present is a tiny fraction of what was there at the beginning. The vast majority of the material that once filled the outer disk has been scattered, absorbed, or lost. The belt that remains is an echo of the original, a surviving sample, a portion that endured. In its surviving fraction, in the specific objects that made it through, in their colors and densities and orbital configurations and paired architectures, the history of the outer solar system is still legible, quietly so, patiently so, without urgency and without any sign of ending. The objects move in their slow orbits. The tholins continue to accumulate, one irradiated molecule at a time. The binary pairs continue to circle each other in the dark, and the mass that is absent, the material scattered and lost over 4 billion years of gravitational upheaval, is present in its own way, as the shape of the emptiness left behind, the space where the early solar system once was denser and fuller and more complete, and from which all that complexity departed without trace, leaving only this quiet, ancient, diminished, and somehow still informative remnant to carry the record forward through the dark and the cold. On the 14th of July, in the year 2015, a spacecraft the size of a grand piano crossed a threshold that no machine had crossed before. It had been traveling for 9.5 years. It had crossed the orbit of Jupiter, the orbit of Saturn, the orbit of Uranus, and the long cold plains beyond. For most of that journey, the object it was approaching showed as nothing more than a pale smear of light against the stars, a point that moved slowly from one image to the next when astronomers compared photographs taken days apart, its details invisible, its surface unknown, its true face unreachable by any instrument on Earth. Then, in the weeks before closest approach, the smear of light began to resolve. It was not fast. It was the kind of resolution that demands patience, a pixel at a time, a day at a time, the shape below the blur, revealing itself the way a room reveals itself when the lights come up very slowly. There was color, there was contrast. Something bright lay in one hemisphere, and the hemisphere around it was darker, and the border between them was not smooth. A world was coming into focus. Pluto had been known as a point of light for 85 years before that morning. Clyde Tombaugh found it in 1930, not by seeing it exactly, but by noticing that a faint dot had shifted position between two photographic plates taken 6 days apart. Everything that moved against the fixed stars was either a planet or an asteroid or something in between, and this dot moved with the slow deliberateness of something very far away. It was catalogued, named, and placed on the map of the solar system at a distance of roughly 39 times Earth's distance from the Sun. For most of the century that followed, it remained that dot. Telescopes improved, instruments improved. Astronomers measured its diameter, estimated its mass, detected nitrogen in its atmosphere by watching it pass in front of a distant star. They found its largest moon, Charon, in 1978 and measured the system's geometry with growing precision, but the surface stayed beyond reach. What arrived in images from that spacecraft, crossing the closest point of its long arc on a July morning, was not what most scientists had expected. Not a cold, dead sphere, smooth and simple and inert. What arrived was a world of startling and ordered complexity, a world of mountains and plains, and flowing ice and layered air, and the long era of imagining Pluto from a distance came to an end. The spacecraft was called New Horizons. It passed within 12,500 kilometers of Pluto's surface. That is close by interplanetary standards, close enough for cameras to resolve features a few kilometers across, close enough for instruments to taste the atmosphere, measure the temperature gradient at different altitudes, map the composition of different surface regions, and distinguish one kind of ice from another. Before the full catalog of images had finished transmitting back across the billions of kilometers of space between Pluto and Earth, a journey that, even at the speed of light, took more than 4 hours each way, the picture of what an outer solar system world could be had already changed. Pluto's orbit is not a circle, it is an ellipse, significantly elongated, tilted 17 degrees out of the plane the other planets occupy. At its closest, Pluto approaches the Sun to a distance of about 29.5 times Earth's distance, briefly passing inside the orbit of Neptune for roughly 20 years out of every 248. At its farthest, it retreats to nearly 49 times Earth's distance, and the Sun, already diminished at 39 AU, shrinks further still into a point of hard, brilliant light that casts sharp shadows but almost no warmth. The elongation of that orbit is not random. Pluto is locked into a precise gravitational relationship with Neptune, a relationship so exact that the two bodies, though moving through the same region of the solar system, have never approached each other closely and never will. For every 2 times Pluto completes one orbit, Neptune completes exactly 3. The timing means that whenever Pluto passes closest to the Sun, and therefore crosses Neptune's orbital path, Neptune itself is far away, on the opposite side of the solar system, more than 2 billion kilometers distant. The geometry repeats with such mathematical regularity that it has held for billions of years, and it will hold for billions more. This relationship is called a mean motion resonance, and it is what has allowed Pluto to remain in its orbit across geological time. Without it, the gravitational pull of Neptune, accumulated orbit after orbit over billions of years, would have perturbed Pluto's path beyond recovery. The resonance does not eliminate the perturbation, it regularizes it so that each tug arrives at the same point in the cycle and cancels the one before. It is a kind of stability written into the structure of time. Pluto was the first of many objects discovered in this resonance. The ones that followed, the ones found in that same 3, to gravitational lock with Neptune, came to carry the name Plutinos, borrowing from Pluto the prototype they shared. Pluto, discovered as a planet in an era before anyone knew there were other bodies like it, turned out to be the first known member of a whole family. The surface that New Horizons revealed in those July images is divided into regions as distinct from one another as any terrain on Earth. The most striking feature is a pale, roughly heart-shaped expanse in the southern hemisphere, bright enough to be visible even in early low-resolution images. It was named Tombo Regio, after the astronomer who spent months searching for it in photographs and recognized it as something new. The western lobe of that heart, the brighter, smoother, younger lobe, is a plain of nitrogen ice. It occupies a large basin, likely the scar of an ancient impact, and its surface is almost entirely free of craters. An absence of craters in planetary science means youth. Something has been erasing the evidence of old impacts. The surface is, in geological terms, extraordinarily recent. Some estimates place its youngest regions at fewer than 10 million years old, which is a very short time against the 4 billion year age of the solar system. This plane was named Sputnik Planitia. What keeps it young is motion. Nitrogen ice, unlike water ice, flows at temperatures near absolute zero. It is not rigid. It responds to even the faint internal heat rising from Pluto's interior, heat left over from the decay of radioactive elements in the rock below, by moving. And because the basin in which it sits is deeper at the center than at the edges, and because nitrogen ice is slightly less dense than the rock beneath it, the material organizes itself. The surface of Sputnik Planitia is divided into polygonal cells. They are large, each one somewhere between 20 and 40 kilometers across, and their boundaries are subtle ridges, slightly raised at the edges, slightly lower at the centers. These are convection cells. Warmer material at the bottom of the nitrogen layer rises slowly through the center of each cell, spreads outward as it cools, and sinks at the edges, only to be warmed again and rise once more. The cycle takes a very long time. Each full overturn of a cell is estimated to take somewhere in the range of 500,000 years. That is slow enough that no human observer will ever see the motion directly. But the effect of all those 500,000 year cycles accumulated over the age of the solar system is a surface that has been stirred and restirred, the way a very slow, very patient hand stirs something thick and cold, and every crater that ever formed on it has been dissolved back into the white. Beyond the edges of Sputnik Planitia, the terrain is ancient and battered. The mountains begin close to the boundary. They rise steeply, some of them reaching heights of 3,500 meters, which is comparable to peaks in the Rocky Mountains. Though Pluto's reduced gravity makes the comparison feel different when measured in any other way. These mountains are not made of the nitrogen ice that covers the plains. They are made of water ice. Water ice on Pluto behaves like rock. At the temperatures that prevail there, temperatures far below anything in the inhabited parts of the world, water ice is rigid, immovable, strong. The mountains stand because their material is strong enough to stand. The nitrogen ice beneath them is not. Nitrogen ice at those temperatures is soft, plastic, a slow-moving substrate. The mountains of Pluto are blocks of water ice resting in a nitrogen plane, and the combination is stable. Their origin is not entirely settled. The current picture suggests they may have been pushed up from below, or may represent ancient crustal material exposed by erosion and flow over geological time. Some of the mountain structures elsewhere on Pluto's surface, rounded, irregular constructs in a region called Right Mons and another called Picard Mons, may be the product of cryovolcanism, a process in which a world's interior erupts not molten rock, but a slurry of water and ammonia, frigid by any inner solar system measure, but warm enough relative to Pluto's surface to flow before refreezing into new terrain. Whether those constructs are truly cryovolcanic in origin is a question the data from New Horizons supports, but does not definitively close. The shapes are right. The scale is right. The absence of clear impactors or other explanations leaves the hypothesis standing, but the fine detail that would confirm it, subsurface imaging, seismic data, the kind of evidence that would come only from a lander, was not something New Horizons could provide from its single, brief flyby. Pluto has an atmosphere. It is thin beyond easy intuition. The pressure at the surface is roughly 100,000 times less than the pressure of Earth's air at sea level. A person standing on Pluto's surface would find the atmosphere as unbreathable as vacuum and almost as close to it. But the atmosphere is there, and it is structured, and it does things. It is composed mostly of nitrogen, with traces of methane and carbon monoxide. Methane absorbs sunlight and warms the upper atmosphere, producing a temperature inversion. The air above a certain altitude is warmer than the air below, the reverse of what happens on Earth. The methane and nitrogen interact under ultraviolet radiation and produce tholins, those same dark organic compounds that color the surfaces of KBOs across the belt. And the tholins settle slowly downward through the atmosphere as fine particles, coating the darker regions of Pluto's surface in their characteristic red-brown. As New Horizons looked back at Pluto from the far side of its closest approach, the spacecraft turning its cameras back toward the world it had just passed, it captured Pluto in silhouette against the distant stars, the sun behind it. In that backlit geometry, the atmosphere became visible as a thin arc of light around the planet's limb. Not one haze layer, but many, concentric, stacked, reaching to altitudes of 200 kilometers above the surface, each layer a different density of atmospheric particles catching the scattered light. The color of that arc was blue. In backscattered light, the tholin haze particles scatter shorter wavelengths, the blue end of the spectrum, in the same way that Earth's nitrogen scatters sunlight to make the sky blue from below. Pluto, photographed in silhouette from below its own atmosphere, has a blue haze ring seen from that angle. In that geometry, in the specific light of that one January morning in the outer solar system, it was an image unlike anything that had come before it. A small, cold, distant world, backlit by a sun, reduced to a brilliant point, wrapped in a thin blue glow. The atmosphere of Pluto is not stable across time. As Pluto moves along its eccentric orbit, its distance from the sun changes substantially. Near perihelion, the closest point, the surface warms slightly, and nitrogen ice near the equator and in sunlit regions sublimates, turning directly from solid to gas and adding to the atmospheric pressure. As Pluto recedes toward the far point of its orbit, the surface cools, the pressure drops, and nitrogen that was atmospheric months before begins to condense back onto the ground. Over the full 248-year orbital cycle, the atmosphere may thin dramatically, possibly freezing almost entirely back to the surface during the long cold years far from the sun, then slowly rebuilding as the world approaches again. The timescale of that breathing is long. No human has ever watched a full Pluto year. The world has not completed one orbit since Tombaugh first recognized it in those photographic plates. Charon is the largest of Pluto's 5 known moons, and its relationship with Pluto is unlike any moon-planet relationship in the inner solar system. It is large relative to Pluto, about half its diameter, and the two bodies are close enough and massive enough relative to each other that their shared center of gravity, their barycenter, does not lie inside Pluto. It lies in the empty space between them. Both bodies are tidally locked to each other. Pluto always shows the same face toward Charon. Charon always shows the same face toward Pluto. They orbit their shared midpoint in perfect synchrony, one face of each body permanently facing the other across roughly 19,500 kilometers of cold space. Charon's surface is darker overall than Pluto's, and marked in ways that suggest a different geological history. It has canyons, it has cratered plains, and at its north pole there is a large dark reddish-brown region that bears a stark visual contrast to the pale icy terrain surrounding it. That dark polar cap is called Mordor Macula, and its color comes from tholins. But the tholins that color Charon's pole did not form there from Charon's own surface ices. Charon, too cold and too small to hold a significant atmosphere of its own, has no sufficient supply of methane at the surface to produce them locally. What happened is different and stranger. Methane escapes from Pluto's atmosphere. The gas drifts outward, away from Pluto, carried by the pressure gradient of a thin atmosphere into space. Some of it drifts far enough, slowly enough, that it reaches Charon. Charon's pole, in the long winter when it faces permanently away from the sun, drops to temperatures where methane freezes directly onto the surface. Over millions of years, methane builds up at Charon's pole. Thin layers, frost-like, but accumulated over such enormous spans of time that the deposit becomes substantial. Ultraviolet radiation from the sun strikes that frozen methane and drives the same chemistry that operates across the surfaces of KBOs everywhere in the belt. Simple molecules rearrange into complex ones. The complex molecules are dark and reddish. They do not resublime when Charon's pole returns to sunlight. They are too stable for that, locked into long-chain organic structures that persist across the polar seasons, building up over geological time into the dark cap that New Horizons photographed. The methane that colored Charon's pole left Pluto. It crossed the space between two gravitationally bound worlds. It settled at the coldest point of the smaller body, was changed there by radiation, and became something new. Chemistry moving slowly between two worlds, molecule by molecule, over millions of years. Not fast, not dramatic, but real and ongoing and visible now in the images returned from a single flyby. 9.5 years in the making. In the decades before New Horizons reached Pluto, a debate had grown in the scientific community about what Pluto was. When it was found in 1930, no one knew what to compare it to. The next object beyond Neptune, beyond Pluto, which for most of the 20th century was assumed to be alone in the outer solar system, would not be discovered until 1992. When it was, and when the objects following it began to accumulate into a recognizable population, the question of Pluto's nature changed. Pluto was not, it turned out, an anomaly. It was not the last lonely outpost of a planetary system that otherwise ended at Neptune. It was the first discovered and largest known member of a vast population of icy bodies that stretched outward from roughly 30 to 50 times Earth's distance from the sun and beyond. Some of those bodies were large. Several exceeded 1,000 kilometers in diameter. One, found in 2005, appeared to be approximately Pluto's size, or possibly slightly larger. The discovery of that body forced a formal decision that had been deferred for decades. The International Astronomical Union, meeting in 2006, defined for the first time what the word planet meant in formal terms. A planet had to orbit the sun. It had to be massive enough for its own gravity to pull it into a roughly spherical shape, and it had to have cleared its orbital neighborhood of other debris, meaning its gravity had dominated the region, either by absorbing other objects, ejecting them, or capturing them as moons. Pluto had not cleared its neighborhood. Its orbit shares the three: two resonance zone with dozens or hundreds of other objects. The region around its orbit is populated with other KBOs, some of them nearly comparable in size. By the new definition, Pluto was reclassified as a dwarf planet. The reclassification was publicly contested in ways that few astronomical decisions ever are. People had grown attached to Pluto's status. it had been a planet for 76 years. For many people alive in 2006, it had always been a planet, and removing it from that category felt like a loss. But the decision did something that no alternative could have done as cleanly. It gave Pluto back its context. Not alone, not anomalous, not an awkward small planet at the edge of the solar system, but the prototype, the first found, the largest known member of a whole class of worlds. A dwarf planet in a belt of icy dwarf planets, each one carrying its own surface and its own story, none of them less real for belonging to a class rather than standing apart from one. The name Plutino, given to the family of KBOs sharing Pluto's orbital resonance, reflects that belonging. There is a family resemblance to being locked into that three. Two relationship with Neptune, a shared rhythm, a common fate, a population sculpted by the same ancient migration of the outer planets that shaped the belt as a whole. Pluto did not lose membership in anything when it was reclassified. It gained it. The images that came back from New Horizons over the months following the flyby showed a world that had not needed the title of planet to justify its complexity. Pluto had nitrogen glaciers. It had evidence that nitrogen ice from the surrounding highlands flowed slowly down slope and pooled in the basin of Sputnik Planitia, the way a terrestrial glacier flows from mountain snowfields into a valley. The directions of flow could be read in the ice, streaks and alignments pointing toward the center of the basin, converging from all sides. Beyond Sputnik Planitia, the surface became irregular. There were bladed terrains, ridges of methane ice, standing in parallel rows, several hundreds of meters tall, shaped by a cycle of sublimation and redeposition driven by Pluto's seasons. There were dark red regions at the equator where tholins had accumulated over long periods of irradiation. There were crater fields in the ancient highlands that told something about the history of impactors in the outer solar system, not as many as some models predicted, which meant either that the population of small impactors in the Kuiper Belt was lower than expected, or that resurfacing had erased more craters than was obvious. Every region that New Horizons imaged carried a different character. The diversity of a single small world over 4 billion years in the cold and the dark had produced terrain types that no one had anticipated and no planetary model had predicted in their specific form. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, orbit farther out than Charon, in nearly circular paths that are broadly consistent with formation in a single large impact early in solar system history, when a massive collision with a roughly Pluto-sized body may have thrown debris into orbit that later assembled into the moon system. The system's geometry, with all 5 moons orbiting in the same plane as Pluto's equator, supports that picture. The moons are small. Hydra, the largest of the 4, is irregular and small enough that its own gravity cannot pull it into a sphere. They tumble, unlike Charon, which has had enough gravitational interaction with Pluto to become tidally locked. The smaller moons rotate in patterns that do not align with their orbital periods, and the interactions among all 5 moons, each perturbing the others in slightly different ways, make some of their rotations essentially unpredictable over long timescales. There is a small, persistent warmth in how the Pluto system is constructed. The 2 large bodies permanently facing each other, the smaller moons orbiting in the shared equatorial plane, tumbling in their own uncoordinated rhythms. The methane moving from one world to the other across open space over millions of years, settling at the pole, being transformed, building up a dark cap that records the transfer, the glaciers flowing inward from the surrounding heights. the convection cells turning over in their slow half-million-year cycles. All of this at 39 times Earth's distance from the Sun, in temperatures far below any that occur naturally on the inner planets, lit by a sun reduced to roughly 1,000th of its brightness at Earth's distance. The Sun, as seen from Pluto's surface, would appear as an intensely bright star, not a disk, not a warm presence the way it is experienced from Earth, but a single point of concentrated light, sharp enough to cast shadows, insufficient to provide warmth, surrounded by stars, no different in kind from the stars in every other part of the sky. Midday on Pluto would be darker than twilight on Earth. In that dim, cold, clear light, the water ice mountains would cast sharp shadows across the nitrogen plains. The haze layers would scatter what light there was into a thin, diffuse illumination from all directions at once. The convection cells of Sputnik Planitia would be slowly moving, invisibly, their time scale so long that a human observer would see nothing but stillness and pale white. It is a quiet world. The atmosphere is too thin for sound to carry in any meaningful way. The temperature is low enough that almost everything that could sublimate or flow does so only on geological timescales, and the result is a surface that, from moment to moment, appears frozen in place. But the apparent stillness conceals a long and active history. Below the nitrogen plains, there is rock. Below the rock, possibly, there may be liquid water, a subsurface ocean, kept liquid by the decay of radioactive elements in the core, insulated by the rock and ice above. The evidence is suggestive, not confirmed. The way the surface topography has responded to internal stresses, the way Sputnik Planitia may have reoriented Pluto's rotation by acting as a gravitational anomaly that slowly drifted to align with the tidal axis between Pluto and Charon. These are consistent with a liquid interior, but not proof of one. Whether liquid water persists beneath Pluto's surface is an open question. The best current picture allows for it. The fine steps that would confirm it, measuring Pluto's tidal response, imaging subsurface structure, studying the chemistry of any material that might have erupted from within, would require a mission that has not yet been launched. What New Horizons gave was a first look, complete in the sense that no surface image at that resolution had existed before, and incomplete in the sense that a single flyby, however well instrumented, cannot answer everything a world has to say. The data it collected will be analyzed for decades. Questions it raised will guide the design of instruments that may one day answer them. Pluto, as seen by New Horizons, is not the last word on Pluto. It is the first word in a new language, the language of a world rendered visible, rendered real, rendered complex, after 85 years of being a point of light moving slowly against the stars. Clyde Tombaugh, who found it in 1930 by the slow, patient comparison of photographic plates, died in 1997. A small portion of his ashes traveled aboard New Horizons and passed through the Pluto system on the 14th of July, 2015, continuing outward into the space beyond. What he found in those black and white plates was not the small anomaly it seemed. It was a dwarf planet with nitrogen glaciers and water ice mountains and a thin blue haze, and a dark moon with an organic polar cap built molecule by molecule from gas that drifted across the space between two tidally locked worlds. It was the first member of a population of thousands. It was a prototype, not of smallness or marginality, but of the kind of geological richness that cold and time and the slow decay of radioactive elements can produce even at the very edge of the solar system's warmth. Pluto belongs to the Kuiper Belt, the way the first found shell on a long beach belongs to the beach, not as a symbol of isolation, but as the first evidence of how much more the beach holds. The orbital resonance that locks Pluto into its 3-2 relationship with Neptune holds it not in constraint, but in a kind of order. The same gravitational arrangement that prevents Pluto from approaching Neptune also prevents Neptune from dismantling Pluto's orbit over billions of years. The resonance is protection as much as it is a lock. Pluto moves in its long ellipse, closer and then farther, passing inside Neptune's orbit and back out, the geometry repeating itself with mathematical patience across time. In the images from New Horizons, the heart-shaped brightness of Tunbul Regio, named for the man who found the point of light and never knew what lay beneath it, glows pale against the darker surrounding terrain. The plane within it, Sputnik Planitia, slowly overturns. The mountains stand. The atmosphere breathes in and out across the 248-year cycle, and Pluto continues in its orbit, in its resonance, in its family, the slow tick of the same gravitational clock that structures the whole outer belt marks its passage. 2 of Pluto's orbits for every 3 of Neptune's, repeated without interruption, since before any of the inner planets had cooled, a rhythm that holds and will hold long after the images from a single July morning have been studied to their last detail, and every question they raised has found its answer or its rest. In the deep archive of telescope images recorded in the late days of the last century, a point of light moved. It moved slowly, almost imperceptibly, against the fixed scatter of background stars, a drift so slight that no single night's observation would reveal it. Only by comparing images taken days apart, holding them against each other like transparencies on a light box, could any eye find it, a pale point tracing a long, slow arc through the outer dark. And the astronomers who found it in January of 2005, Mike Brown, Chad Trujillo, and David Rabinowitz, working through years of archived sky surveys from an observatory in the California mountains, did not at first know what they had. They knew its distance. They knew it was far, roughly 3 times further from the sun than the classical outer edge of the Kuiper Belt. They knew it was bright, which at such distances meant it must be large. What they had, without yet naming it, was a world, a dense, pale, cold world, drifting at the outermost margin of anything the solar system had shown them before. That world would be called Eris, and its discovery, in the quiet data of archived sky surveys, would force a question that the solar system had been holding in reserve for decades. If the outer dark contained a world as large as Pluto, perhaps larger, what else was there? Eris moves in a long ellipse. At its farthest point from the sun, it reaches nearly 97 astronomical units out, nearly 100 times the distance from the Earth to the sun, a distance so vast that sunlight arriving there is 10,000 times fainter than the sunlight that falls on us. At its closest, its orbit draws it to within about 38 astronomical units, just brushing the inner edge of the classical Kuiper Belt. The full circuit takes roughly 559 years. In the time it takes Eris to complete a single orbit, Rome rose and fell, the printing press was invented, and every nation now on Earth was born. The world turns its long ellipse in silence, in the cold, reflecting the distant sun off a surface coated in methane ice, so bright and unweathered that it is one of the most reflective bodies in the outer solar system. Its diameter sits close to 2,300 kilometers, within measurement of Pluto's own width, but it is denser. Where Pluto is a mix of rock and ice, loosely packed, Eris carries more rock than ice at its core, giving it a density roughly 2.5 times that of water, and a weight of compressed material that tells of a body more compacted, more differentiated, more geologically sorted than its apparent twin in the inner belt. A small moon, dysnomia, accompanies it. From the careful measurement of dysnomia's orbital period and separation, the mass of Eris was calculated precisely, and that mass confirmed what size alone had suggested. This was a world, not quite a planet by any working definition the scientific community would ultimately settle on, but not a minor body either. It was something the outer solar system had been harboring in silence, on its long, slow ellipse, waiting to be found. Its discovery did not change the Kuiper Belt. The belt was what it had always been. What changed was the picture humans held of it, the realization that the population beyond Neptune was richer, stranger, and more varied than any single famous world could represent. The outer solar system was not a solitary cold place with one notable object and a surrounding field of debris. It was a community of worlds, and Eris was only the most distant of those that had been large enough to name. Some of those worlds are bright, some are dark, some spin slowly in the long silence, others move with a restlessness that has left visible marks on their bodies. Make holes one of the bright ones. Its surface carries a coating of methane and ethane ice that reflects the sun with an efficiency close to that of freshly fallen snow, giving it an albedo, a measure of how much light it returns, of roughly 77%. Most rocky bodies in the solar system absorb most of the light that falls on them. Makehol's coal dung gives nearly all of it back. At its distance of roughly 46 astronomical units, the sunlight it reflects is faint enough that even with that high reflectivity, Makehol's coal dung has a dim pinkish point, its redness a sign of tholins on its surface, complex organic molecules built slowly over billions of years. When ultraviolet radiation and high-energy particles from the sun struck its simpler ices and rearranged them into something darker, something more chemically intricate. In 2011, astronomers watched Make pass in front of a distant star. For a fraction of a second, the star's light dimmed and vanished, and then returned. The timing and the shape of that disappearance told them something that could not be read from its brightness alone. Make, unlike its better-known counterpart Pluto, carries no significant global atmosphere. The starlight did not dim gradually at the edges of the occultation, the way it does when a world's atmosphere bends and filters the light, on the way in and on the way out. It cut off sharply. The surface is exposed directly to space, its ices in contact with near vacuum, its temperature close to 30 degrees above absolute zero. Whatever volatile gases might have risen from that surface in Mike Make's warmer past, when its elliptical orbit carried it closer to the sun and the ices at its surface grew warm enough to sublimate, they did not remain. The atmosphere, if it ever assembled, collapsed back onto the ice long before any human thought to look. That absence is its own kind of record. Pluto holds its atmosphere, thin as it is, because of the particular conditions of its orbit and the large nitrogen reservoir of Sputnik Planitia. Make does not share those conditions. Same class of world, different history, different result. The diversity within the Kuiper Belt is not a disorder. It is the signature of small differences in starting position, in composition, in size and density, and orbital shape, amplified over 4 billion years into outcomes that look at first quite unrelated. Then there is Haumea. It is not round. Most large bodies in the solar system, given enough mass and enough time, pull themselves into spheres under the force of their own gravity. Gravity, acting equally in all directions, draws material inward and levels any surface irregularity above a certain scale. Haumea is large enough that this process should have made it spherical. Instead, it is a prolate ellipsoid, elongated, stretched, shaped something like a rugby ball or an American football, measuring roughly 2,100 kilometers along its longest axis and only about 1,070 along its shortest. The shape is not an accident of formation, it is the consequence of speed. Haumea rotates once every 3 hours and 56 minutes. For a body of its size, more than 1,300 kilometers in radius along its longest dimension, that is extraordinarily fast. The centrifugal effect of that rotation, the outward pull that results from spinning, has forced the body's material outward along the equator, stretching it into the elongated form that is now visible from Earth through careful photometric measurement. The brightness of Haumea, as seen from Earth, rises and falls on a regular cycle as the body spins, showing first a wider face and then a narrower one, and from those variations in brightness, the rotation period and shape were reconstructed with remarkable precision. What set Haumea spinning so fast is not entirely settled. The best current picture is that a large collision early in the solar system's history, an impact significant enough to have shed material into space, transferred angular momentum to the body, and set it rotating at the speed it maintains today. The material thrown outward by that collision assembled into two small moons, Hyakka and Namaka, which orbit Haumea in distinct paths. Some of that same material may have spread more widely into the belt, producing a population of Haumea family members, objects with similar orbital properties and surface compositions that appear to trace a lineage back to the same ancient impact. In January of 2017, Haumea passed in front of a distant star. Astronomers at more than a dozen observatories across Europe watched the event simultaneously, timing the star's disappearance and reappearance with precision measured in fractions of a second. From those measurements, the shape of Haumea was confirmed with a degree of accuracy no direct imaging could then match. And something else appeared in the data. Before the star's light cut off completely, before Haumea's solid body blocked it, the light dimmed briefly, recovered, then dimmed again in a narrow symmetrical signature on either side of the main event. Something else was there, encircling Haumea at a distance of roughly 2,287 kilometers from its center. A ring around a Kuiper Belt object, was not something the theoretical models of the outer solar system had predicted with any confidence. Rings in the established picture were the province of the giant planets, Saturn's great system, the fainter rings of Uranus and Neptune, the thin ring of Jupiter. A small, fast-spinning icy body in the outer belt was not where the models had pointed. And yet the data was unambiguous. The dimming pattern was real and symmetric and repeatable in every observatory's record. Haumea carries a ring, narrow, dense for its kind, and tilted to orbit roughly in the plane of Haumea's equator. The ring circles the spinning, stretched body in silence, a structure known entirely through the mathematics of shadow, through the careful subtraction of a star's brief, precise disappearance. The ring is thought to be held in shape partly by the gravitational influence of Haumea's non-spherical form, which creates resonances in the orbits of nearby particles. But the details of its maintenance, why it persists as a distinct narrow band, rather than spreading and dispersing over the time scales of billions of years, are still being worked out. The ring exists. The full account of why it exists the way it does remains a problem. The field is still turning over. Beyond Haumea, Beyond even the far orbit of Eris, the Kuiper Belt holds objects of a different character altogether. Small, cold, undisturbed bodies that have never been significantly altered by gravitational stirring, never thrown outward from a different origin point, never warmed enough to lose their most volatile ices or develop the atmospheric complexity of larger worlds. The cold classical belt, the quietest region of the Kuiper Belt's broad population, is home to these bodies, and in that quiet region, at a distance of roughly 44 astronomical units from the Sun, a small world drifted in its gentle near-circular orbit for more than 4 billion years before a spacecraft found it. Its name is Arakoth. In the language of the Powhatan people of the Tidewater region of eastern North America, the word means sky. It was given that name in 2019 after the flyby that first resolved it from a point of reddish light into a shape, a specific, improbable, beautiful shape that no model of solar system formation had explicitly predicted, and that every model of solar system formation was quietly suggesting. The New Horizons spacecraft, after its close passage through the Pluto system, continued outward. It did not stop. It could not stop a spacecraft in interplanetary space, absent a propulsion system powerful enough to break against the sun's remaining pull at that distance, simply continues in the direction its velocity carries it. New Horizons had been directed after Pluto toward a specific target, a cold classical KBO, whose pre-encounter catalog designation was 2014 MU69, chosen partly for its distance and accessibility given the spacecraft's remaining fuel, and partly because its orbital properties, nearly circular, low inclination, undisturbed, made it one of the most representative objects of the cold classical population available for encounter. In the months before closest approach, images from New Horizons showed 2014 MU69 as a point of light, then as a slightly elongated blur, and then, in the hours before the January 1st, 2019 flyby, as something recognizable. The blur had two lobes in contact, two rounded bodies pressed together at a gentle neck, forming a shape that planetologists call a contact binary, a pair of objects that once orbited each other at close distance and slowly, gradually spiraled inward until they touched. The closer lobe, Ultima, is larger. The smaller lobe, Thule, is a flattened spheroid about 15 kilometers across. Together, end to end, they span approximately 36 kilometers, small enough that the entire object would fit comfortably within a mid-sized terrestrial city. From New Horizons cameras, the surface appeared uniformly dark reddish-brown, colored by the tholins that have been accumulating on cold classical KBO surfaces for the entirety of the solar system's history, and it appeared smooth, not featureless. There were subtle mounds, shallow depressions, what might be interpreted as the collapsed remnants of smaller subunits within each lobe, but smooth in the sense that craters were scarce, and the terrain did not carry the heavily impacted, time-worn surface that older, more disturbed bodies tend to accumulate. The scarcity of craters on Arakoth is itself a record. At 44 astronomical units, impact rates are low. There is simply less material in the cold classical belt to collide, and what is there is moving slowly relative to the speeds that dominate in the inner solar system. But the smoothness of the surface, even accounting for the low impact rate of the cold outer belt, suggests that Arakoth has been largely unchanged since the early period of solar system formation. Its surface is as close to primordial as anything yet examined directly. The contact binary shape is the most significant datum Arakoth offers. Two lobes that form together in the same local cloud of debris, from the same fine-grained material, and that slowly drew each other in, not through a high-speed collision that would have shattered both, but through a slow, patient gravitational courtship that ended in the gentlest possible merger. The neck between the two lobes is smooth and unbroken. There is no sign of shattering, no rubble scattered outward, no fractured surface at the point of contact. They met softly, they held. The model that best explains this kind of formation, two similar co-formed bodies slowly merging in a gentle embrace, is called streaming instability. In the early solar nebula, before any large planetesimals had assembled, the gas and dust in the outer disk were not evenly mixed. Local concentrations could spontaneously form. Regions where dust particles, for reasons related to the fluid dynamics of the gas-dust mixture, began to cluster together in thin streams or sheets. Within those concentrations, self-gravity among the dust grains was strong enough to pull a local cloud into collapse, not a single central body, but sometimes a binary or multiple system, with the two main concentrations orbiting each other as they continued to accrete material from the surrounding cloud. Over the slow time of the early solar system, those two orbiting concentrations would gradually lose energy to tidal forces and draw together, eventually settling into a contact binary, precisely the structure New Horizons found at 44 astronomical units from the Sun on the first day of 2019. Arakoth is not proof that streaming instability was the dominant formation mechanism for all cold classical KBOs, but it is the most direct observational evidence yet obtained that the mechanism operates in the real solar system, not just in computer models. Before Arakoth, the evidence for streaming instability was largely theoretical, supported by the statistics of binary populations and the general properties of cold classical objects. After Arakoth, a specific examined body showed a structure that streaming instability naturally produces and that alternative formation mechanisms struggle to explain without invoking processes that would leave different marks on the surface. The marks that are there are the marks of a slow, cold, gentle origin, the marks of patience. Further out still, among the scattered disk objects and the extended scattered disk, other bodies trace their long, lonely ellipses. Most of these will never be visited by any spacecraft in any human lifetime. They are known as points of light, as orbital arcs reconstructed from observations taken months or years apart, as brightness measurements and crude spectral classifications and the bare mathematics of their trajectories. But one among the scattered population stands apart not for what is known about its surface. Very little is known about its surface, but for what its orbit implies. The world is called Quaoar. It orbits the Sun at a distance of roughly 43 astronomical units in the outer classical belt, in a roughly circular path that keeps it within the familiar confines of the Kuiper Belt's classical population. It is moderately large, perhaps 1,100 kilometers in diameter, large enough to maintain a roughly spherical shape under its own gravity, and possibly large enough to have separated internally into a rocky core and an icy mantle, though confirmation of that structure awaits better measurements. Its surface is reddish. It carries a small moon, Waywat, discovered in 2006, whose orbital properties allow estimates of Quaoar's mass and density. In 2023, observations confirmed what earlier data had suggested. Quaoar possesses a ring, a narrow, dense ring circling the body at a distance of roughly 4,100 kilometers from its center, approximately 5.5 times Quaoar's own radius. That distance matters. Every large planet with a ring system in the solar system carries its rings within a region called the Roche limit. the distance inside which tidal forces from the central body are strong enough to tear apart any loosely bound aggregate of material. Within the Roche limit, material that might otherwise clump together into a moon is prevented from doing so by those tidal forces, and so it persists as a ring. Beyond the Roche limit, tidal disruption weakens, self-gravity within any local concentration of ring particles becomes dominant, and the material should gradually coalesce, should over time assemble into a moon. Rings outside a body's Roche limit should not persist indefinitely. They should coalesce and disappear. Quaoar's ring sits well outside its Roche limit. By the conventional calculation, it should have coalesced into a small moon long ago. It has not. It persists, narrow, dense, stable appearing, in a location where conventional ring physics says a ring should not be. The explanations currently proposed are several, and none has been confirmed. One suggestion involves the temperature of the ring particles. At Quaoar's distance from the Sun, the surface of any small icy body is cold enough that collisions between ring particles might be more elastic, more bouncy, in informal terms, than they would be closer to the Sun, where warmer, softer ice would cause colliding particles to stick together more readily. If the particles in Quaoar's ring are cold enough and rigid enough to bounce off each other without coalescing, the ring could persist without the support of the Roche limit's tidal forces. Another suggestion involves orbital resonances with Waywat, which might confine the ring particles and prevent them from spreading into a dispersed cloud or clumping into a moon. The details remain unresolved. What Quaoar offers in the end is the same thing the Kuiper Belt has been offering since the first object beyond Pluto was found in 1992, an observation that fits imperfectly into the existing picture and that quietly requires the picture to grow. Not a crisis, not a refutation of everything previously understood, simply a ring where a ring should not be, persisting in cold silence at 43 astronomical units, circling a body that is itself only partly known, in a region of the solar system that is still being mapped. The belt holds these worlds in its broad, quiet band, Eris on its long, eccentric ellipse, spending centuries in the extended dark beyond the classical belt's outer edge, before swinging slowly, slowly back through the outer regions, and out again. Make, bright and atmosphereless, reflecting the distant sun off its methane ice surface, while the irradiation-built tholins darken its older terrain. Haumea, spinning fast in its elongated shape, ringed by a narrow band of material that encircles it in the plane of its equator, attended by two small moons that carry the signature of an ancient impact. Arikoth, at rest in its gentle near-circular orbit at 44 astronomical units, its two lobes in slow contact since the early solar system, its reddish surface unmarked by the violence that shaped noisier regions of the belt, and Quaoar carrying its anomalous ring in a silence that does not yet have a full explanation. These are not curiosities at the edge of the familiar. They are part of the same vast structure that formed 4.5 billion years ago from the cold outer regions of the solar nebula, where water first froze into crystal and methane condensed into ice, and the building material of the belt accumulated grain by grain across the long dark distance beyond Neptune. Each of these worlds formed from that same population in that same cold disk, under the same ancient conditions. The differences between them, in size, in composition, in orbital shape, in the presence or absence of atmospheres, and rings and moons, are the record of small variations in initial conditions, amplified across the whole of geological time. The cold is the common thread. At these distances from the sun, the temperature of a body's surface rests somewhere between 20 and 50 degrees above absolute zero, colder than the coldest place on Earth, by a margin that human experience provides no real reference for. Liquid water is impossible at these temperatures. Most volatile compounds, methane, nitrogen, carbon monoxide, are solid. The chemistry that takes place on these surfaces is not the fast, fluid chemistry of warmer worlds. It is slow. It is the chemistry of ultraviolet photons striking a frozen surface and rearranging molecular bonds over millions of years. It is the chemistry of cosmic ray particles passing through the outer layers of ice and leaving behind broken fragments that recombine into something more complex, darker, redder than what was there before. Tholins are not made quickly. They are made by the patient accumulation of damage and reorganization over timescales that dwarf the entirety of recorded human history. Their reddish-brown color, visible across the cold classical population as a whole, is geological time made visible. It is 4 billion years of slow chemistry, wearing its result on the surface. The binary systems of the cold classical belt carry their own record of time. Two bodies of similar size, similar color, similar composition, orbiting each other at slow, wide separations. These are not pairs that formed separately and were later captured into mutual orbit. Capture at these low encounter velocities would be extraordinarily improbable. The best current picture is that they formed together from the same local concentration of debris in the early solar nebula, assembled as a gravitationally bound pair before either had grown to final size. They have been orbiting each other ever since. In the cold classical belt, where the environment has remained calm and undisturbed, those wide binary orbits have been preserved across 4 billion years without being disrupted by close encounters or gravitational stirring. In the hotter, more dynamically active regions of the belt, these wide binaries would have been pulled apart long ago. Their survival in the cold classical population is itself evidence of just how undisturbed that region has remained. The cold classical belt is in this sense a kind of museum, not a dead one. The slow chemistry continues. The bodies drift through their orbital cycles. The rare collision still occurs somewhere in the wide dark band, but a museum of conditions, a collection of objects that have been maintained very nearly intact since the era before the solar system reached its current configuration. Their orbital inclinations close to the plane of the solar system, their orbital shapes nearly circular, their colors uniformly reddish, their binary fractions high and distinct from hotter populations. All of these properties together describe a population that has not been significantly touched by the gravitational upheaval that rearranged so much of the rest of the outer solar system. When a new telescope surveys a patch of sky in the outer ecliptic and records the positions and brightnesses of the faint, slow-moving points that are KBOs, it is accumulating data about this population. Each new object added to the growing catalog is another constraint on what the cold classical belt looks like statistically. How many objects there are at each size, how many are binaries, what fraction carry detectable reddening from Tholin chemistry, how their orbital inclinations are distributed. From those statistics, the conditions of the early solar nebula can be inferred, gradually, imperfectly, with the patient work of many observations and many models and the careful accounting of what is measured and what is merely assumed. The outer solar system is large, enormously so. The cold classical belt alone spans a region from about 42 to 48 astronomical units, a band so wide that light, moving at the full 300,000 kilometers per second that it always moves, takes more than 40 minutes to cross it. Within that band, the largest objects are separated from each other by distances of billions of kilometers. The collisions that do occur happen slowly, at low relative velocities, between bodies that have spent most of their existence in quiet isolation. This is a place shaped less by drama than by the long, slow persistence of initial conditions. The objects within it, Arakoth, its unnamed neighbors, the wide binaries drifting in their mutual orbits, the reddened surfaces accumulating tholins in the dark, are not remnants of something that was once more active and has now quieted. They are themselves the quiet. They are what the outer solar system looked like nearly at the beginning, and they carry that resemblance still, after 4 billion years, into the present. Eris traces its long ellipse in the outer dark, cold and pale and dense, its methane ice coating reflecting back the faint sunlight that reaches it across 97 astronomical units of intervening space. Makemake holds its bright atmosphereless surface exposed to the raw ultraviolet of that same distant sun, its tholins reddening the older terrain, while fresh ice glints where new material is exposed. Haumea spins in its elongated form, the narrow ring encircling it in the silence of deep space, and the two ancient moons following their paths, all of it turning, all of it cold, all of it quiet in the way that only things very far from any center of warmth can be quiet. And in the cold classical belt, at 44 astronomical units, Arakoth holds its two lobes in their long-maintained contact, the reddish surface facing the dark in all directions, the sun reduced at that distance to the brightest star in a sky full of stars, a star whose warmth, at 44 times the distance the Earth stands from it, is 1/2000th of what falls on this world on an ordinary afternoon, cold enough that nothing on its surface has changed in any essential way since the solar nebula cooled and cleared and left the young solar system to its long orbital future. Quaoar carries its ring. The ring persists. The question of why it persists remains open, patient, requiring no resolution tonight. These worlds are not at the edge of something. They are part of the full extent of what the solar system is. The familiar planets, the warm inner worlds, the gas giants, these occupy only the inner portion of a structure that reaches much farther than they do, into regions where the temperature of sunlight is barely distinguishable from the temperature of the void between stars, where bodies formed in the same original disk move in orbits so gentle and so undisturbed that their paths today resemble the paths they were born into, unchanged by the 4 billion years of geological time that have passed between then and now. The reddish-brown color of a tholin-coated surface at the edge of the classical belt is a clock. It is time made visible in chemistry, written slowly by sunlight too faint to warm, by radiation persistent enough to transform. Every hour of the solar system's life has contributed one more photon to the rearrangement of those surface molecules, one more cosmic ray particle threading through the outer layers of ice and leaving its small mark behind. The color accumulated in the way that all geological records accumulate, not in any single event, but in the patient arithmetic of deep time, grain by grain, and bond by bond, and year by year, across a duration that dwarfs anything the human mind uses time to measure. Out there, in the quiet of the cold classical belt, that slow accumulation continues. The surface darkens a little further. The binary pairs hold their wide, slow orbits around each other. The tholins deepen from pale pink toward the deeper reds of the most ancient, most undisturbed surfaces, and the whole broad population drifts in its nearly circular paths, tilted close to the plane of the solar system, undisturbed, unhurried, unchanged in any meaningful sense since the world was new, carrying in its slow orbital motions and its chemistry-stained surfaces a memory of conditions that no other part of the solar system has preserved so completely or held for so long. A small dark body, a few kilometers across, moves through the inner solar system with its surface just beginning to warm. For billions of years, it drifted in the cold beyond Neptune, locked in a slow orbit, so far from the sun that the light reaching it was barely stronger than starlight. Then something shifted. A gravitational nudge, small and patient, altered its path by a fraction. Then another nudge, and another, each one the product of a close approach to Neptune, or one of the other giant planets, each one bending the trajectory a little more inward, across the orbit of Jupiter, into the warm interior of the solar system where the sun's heat finally reaches it. The ices on its surface, preserved in cold darkness since the first million years of the solar system's life, begin at last to sublimate. They rise from solid to gas without passing through liquid, streaming outward from the nucleus in jets and plumes. Dust caught in those plumes unfurls behind the body in a tail that stretches for millions of miles, catching sunlight visible from Earth with the naked eye. A comet has arrived, and the journey that ended here, in brightness and spectacle above the inner planets, began in the quiet of the Kuiper Belt, where a small icy body drifted in a wide, slow arc, unchanged, waiting without knowing it was waiting for the nudge that would bring it home. The path a comet travels inward is not a straight line and not a short one. Neptune is the first mover in that sequence, and it reaches these small bodies through the geometry of orbital resonance and close gravitational approach, slowly widening the eccentricity of their paths over millions of years until they cross into the domain of the other giant planets. Jupiter then takes over. Its gravity is strong enough to fling some comets entirely out of the solar system and to redirect others onto shorter, steeper orbits that loop between Jupiter and the inner planets on timescales of years rather than millennia. The comets that travel this shorter path, sweeping around the sun in periods of less than 20 years, are called Jupiter family comets, and they are among the most closely studied objects in the solar system. One of them, a dark, irregular body roughly 4 kilometers at its widest, became the subject of the most detailed comet investigation ever conducted. It is known as 67P, and a spacecraft called Rosetta reached it in 2014 and matched its orbit, flying alongside it for more than 2 years. What Rosetta found was a surface of dust and rubble and volatile ices, of cliffs and pits and smooth flat plains, of jets erupting from specific sunlit regions as the ice beneath them warmed and turned to gas. The nucleus was black as coal. It smelled, had a nose been present to detect it, of sulfur and ammonia and bitter organic compounds. That object, that dark and complicated little world, began its existence as part of the same icy population that fills the space beyond Neptune. It is a piece of the Kuiper Belt, delivered inward by 4 billion years of slow gravitational conversation. The comets that arrive in the inner solar system carry something else with them besides the spectacle of their tails. They carry material that has been sealed in cold storage since the solar system's earliest period, preserved in the outer disk where temperatures were low enough to keep volatile ices intact. Water ice, carbon monoxide, methane, complex organic molecules built up across geological time by radiation acting on simpler compounds in the outer reaches of the solar nebula. When a comet warms and its surface begins to sublime, those materials enter the inner solar system for the first time, some of them for the only time. Spacecraft that have sampled cometary material directly have found amino acids among the organic compounds in the outflowing gas and dust. They have found the same chemical ratios found in meteorites and in Earth's own oceans. The Kuiper Belt is not only the source of periodic visitors to the night sky, it is in part a reservoir of the raw chemistry from which the inner planets were built, and the chemistry that life on Earth is built from. The connection is not metaphor. It runs through physics, through the orbital mechanics that slowly redirect icy bodies inward, through the sublimation that opens them up to the warmth and lets their contents drift free. There is a model of the early solar system that places the Kuiper Belt at the center of one of the most violent chapters in planetary history. Four researchers, Rodney Gomes, Harold Levison, Alessandro Morbidelli, and Cleomenes Tsiganis, published it in 2005, drawing on simulations of how the giant planets would have behaved when the outer solar system was still young and full of small bodies. In those earliest hundreds of millions of years, the giant planets sat closer together than they do today, embedded in a vast disk of primordial planetesimals stretching outward to great distances. Over time, gravitational interactions between the planets and that disk transferred angular momentum slowly between them. Saturn, Uranus, and Neptune crept outward. Jupiter moved inward by a small amount. As Neptune migrated, it swept through the outer disk, scattering most of what it encountered. Some of those scattered bodies fell inward, toward Jupiter, which ejected them from the solar system entirely. The cumulative loss of mass from the disk subtracted angular momentum from the giant planets, eventually bringing them to a point where a gravitational resonance between Jupiter and Saturn was crossed. That crossing drove an instability. The giant planets shifted rapidly to their current configuration. Neptune was flung outward, plowing through whatever remained of the outer disk at high speed, scattering bodies in all directions, capturing some into resonant orbits, and leaving behind the structured but depleted belt that exists today. The model carries a further implication, one written into the surface of the moon. If Neptune's rapid outward migration flung enormous numbers of small bodies inward, many of them would have found their way to the inner solar system, arriving in a surge that would have pocked the terrestrial planets and the moon with craters. The lunar cratering record shows a period of elevated bombardment centered at roughly 3.9 billion years ago, a period scientists call the late heavy bombardment, though whether it was a short spike or the tail end of a longer decline is a question that remains open. The moon cannot tell us everything. The rocks that recorded the earliest part of its crater history have been buried, melted, and remade by subsequent impacts, so the oldest chapters of that record are simply missing. What survives suggests something happened at that time, something that left its mark in the distribution of impact ages across the lunar highlands. Whether that something was triggered by Neptune's migration through the outer disk remains an active question, with real evidence on multiple sides and no settled answer yet. The model is the best current picture of how the giant planets reach their present orbits, and the Kuiper Belt is both the evidence of what happened and the partial record of how it unfolded. Far beyond the classical Kuiper Belt, at distances where even the best current telescopes struggle to see, there are objects whose orbits cannot be explained by any interaction with Neptune currently occurring. One of them, a reddish body named Sedna, was discovered in 2003, moving along an immense elliptical path. At its nearest approach to the Sun, Sedna comes no closer than about 76 times Earth's distance, nearly twice the outer edge of the classical belt. At its farthest, it swings out to roughly 1,000 times Earth's distance, into a region so remote that the sun there would appear as nothing more than a very bright star. A single orbit takes Sedna approximately 11,400 years to complete. No known planet in the solar system can be responsible for an orbit that remote, with a perihelion so far from Neptune's reach. Sedna belongs to what is called the extended scattered disk, a population of objects whose orbits suggest they were disturbed at some earlier time by forces no longer active. Several explanations have been proposed. During the first 100 million years of the solar system's life, the Sun was probably still part of the stellar cluster in which it formed, surrounded by thousands of other young stars in relatively close proximity. A passing star could have perturbed the outer disk, lifting the perihelia of some objects to the distances seen in Sedna's orbit, placing them on paths that have drifted, essentially undisturbed, ever since. Another possibility is that a large undiscovered planet orbits in the distant solar system, its gravity slowly clustering the orbits of the most remote objects into alignments that could, in principle, be detected statistically in the data. The orbital clustering of certain extreme trans-Neptunian objects has suggested something may be perturbing them, but the evidence is not yet sufficient to be certain, and the alternative explanations, observational bias, small sample sizes, remain credible. Sedna and the other extreme bodies like it remain the most remote message the solar system has sent, written in orbital geometry, still being read. The stars in the night sky are not merely points of light in the background. Many of them are orbited by their own belts of icy and rocky debris, by the same kinds of populations that surround the sun, shaped by the same gravitational forces, produced by the same processes of planet formation that filled the outer solar system with the objects of the Kuiper Belt. These structures around other stars are called debris disks, and they are detected not by seeing the individual bodies within them, which are far too small and faint at those distances, but by the infrared light that the dust produced by their collisions emits. A body of dust heated by its star radiates in the infrared beyond what the star alone would produce, and that excess, measured precisely across many wavelengths, reveals the presence of a disk. Roughly 15 to 25% of nearby main sequence stars show this excess, meaning that belts of planetesimal debris are common features of planetary systems, not peculiar to the Sun. Among the best studied of these disks is the one around a star called Fomalhaut, about 25 light-years from the solar system, young and bright and ringed by a narrow band of dust that is offset from the star's center and slightly elliptical in shape. That offset, that gentle eccentricity in the disk's geometry, suggests that something massive and unseen, a planet moving in an eccentric orbit, is gravitationally shaping the ring, confining its inner edge sharply and pulling the whole structure slightly off-center. The same process, writ small, is what Neptune does to the Kuiper Belt's outer edge. The same physics that produced the sharp boundary at 48 astronomical units. The sudden drop in KBO density where Neptune's reach thins the population operates in other planetary systems around other stars, leaving the same signatures in the distribution of dust. The Kuiper Belt is not a unique structure that belongs only to the Sun. It is one example of something that planetary systems produce, in one form or another, as a natural consequence of their formation. Looking at the disk around Fomalhaut from the outside, from a great distance, astronomers see what our own system would look like from the same vantage. A narrow ring offset slightly, bright in the infrared, sharp at the inner edge. They can read from its geometry that something massive is shaping it, They cannot see the individual objects within it. They cannot resolve the bodies the size of Pluto or Eris or Makemake or the smaller ones or the binaries drifting in wide mutual orbits. They see only the integrated signal of a population, the statistical fingerprint of a structure shaped by gravity over time. This is in many ways what astronomers studying the Kuiper Belt spent decades doing, reading a structure from a distance, inferring from the distribution of orbital elements, from the colors and sizes of objects visible at the limit of detection, what the underlying population looked like, how it formed, how it was disturbed. The Kuiper Belt has now been mapped in enough detail that its features, the resonant populations, the cold classical core, the scattered disk, the outer cliff at 48 AU, are understood as a connected whole, each feature a consequence of the same migration that shaped the others. That understanding came slowly, over years of observations by many telescopes, and it is still not complete. In the high, dry air above the mountains of northern Chile, at a site chosen for its darkness and the steadiness of the air above it, a facility is being prepared that will change what is known about the outer solar system more rapidly and more deeply than any previous instrument. The Vera, the 100th, Rubin Observatory is designed to image the entire accessible sky every few nights, accumulating over its planned 10-year survey an archive of light curves, positions, and brightnesses for billions of objects. Among the things it will find are trans-Neptunian objects, the small and distant bodies of the Kuiper Belt and the scattered disk, in numbers that will reshape the field. Estimates suggest it will detect 40,000 or more new trans-Neptunian objects during its survey, compared to the roughly 3,000 currently cataloged. Each new object will contribute its orbit, its brightness, its color if measured, to a statistical sample that will for the first time be large enough to test the fine predictions of planetary migration models. Whether the resonant populations have the sizes predicted by the NICE model's orbital history, whether the binary fraction in the cold classical belt is as high as current estimates suggest, whether there are clustering patterns in the orbits of the most distant objects that point towards something large and unseen in the outer solar system, or whether the apparent clustering dissolves as the sample grows and observational biases are corrected. Many of the questions that today have uncertain answers will, within the span of a decade or two, have better ones. Some questions not yet asked will be revealed by the data itself, as discoveries always reveal new questions alongside answers. The cold classical Kuiper Belt, that band of gently inclined, nearly circular orbits between roughly 42 and 48 astronomical units, is the region that preserves the record most clearly. Those objects never passed close to a planet. They were never heated, never violently scattered, never stripped of their original surfaces by the energies of collision. Their orbits today resemble the orbits they were born into 4.5 billion years ago, shifted slightly by the long, slow drift of gravitational interactions, too weak to disturb, but not too weak to measure. Their surfaces carry the products of billions of years of radiation, of ultraviolet light from the sun, converting simple ices into complex organic compounds, building up that dark reddish crust that spectroscopy reads as the signature of long exposure and chemical patience. Their binary pairs, two similarly sized and similarly colored bodies, moving in slow, wide mutual orbits, record the conditions of the solar nebula at the moment of their formation, the density and velocity distribution of particles in the outer disk, preserved in the mass ratio and separation of two bodies that assembled from the same local cloud, and have not been significantly disturbed since. When astronomers measure the orbital inclinations of the cold classical belt, they are reading the thermal conditions of the outer nebula billions of years ago. When they measure the binary fraction, they are reading the density and dynamics of the particle population from which planetesimals formed. The cold classical belt is a document. Its pages are the orbital parameters of thousands of small bodies, and the language they are written in is the language of gravitational physics, which does not fade or distort over time, which records precisely what happened and preserves that record as long as the objects that hold it continue to orbit. The outer edge of the classical belt, the sharp drop in population density at about 48 astronomical units, is the clearest single feature in that document. It marks the outer reach of Neptune's mean motion resonance influence. Beyond it, the orbit of a small body is no longer periodically reinforced against disruption by the pattern of gravitational nudges that resonances provide. Objects beyond that boundary are less stable. Over long time scales, they drift out of the region. The belt ends not because the solar nebula ended there, it almost certainly extended farther, but because Neptune's gravitational reach, operating across billions of years, cleared the region beyond with sufficient efficiency to produce a sharp, well-defined boundary. That boundary is carved by the same force that produced the resonant populations, that captured the Plutinos into their 3-2 rhythm with Neptune, that filled the 2-1 resonance at roughly 47.8 astronomical units, that stirred the hot classical population to higher inclinations and eccentricities as it passed through. Every feature of the Kuiper Belt's architecture connects back to that migration, to Neptune's slow outward movement through the early outer disk, and the boundary at 48 astronomical units is the outermost clear sign of where that influence was strongest and most lasting. Within the belt's cold classical core, a small body drifts on an orbit that has not changed in any significant way since the formation of the solar system. Its surface is dark and reddish. It is perhaps 200 kilometers across, a rubble pile held together by the gentle pull of its own gravity, assembling very slowly from smaller fragments that came together at low speed in the low-density outer disk. It is probably not alone. A companion body, similarly sized and similarly colored, orbits it at a wide, slow separation, the two of them completing a mutual revolution over the course of several weeks, their shared center of mass tracing a nearly circular path around the sun in the cold and dark. They formed from the same local cloud. They have orbited each other, essentially, since that cloud collapsed. Nothing in 4.5 billion years has been energetic enough to separate them or to alter the inclination of their mutual orbit significantly. They carry in the precise angle of that orbit and the ratio of their masses a record of the conditions from which they formed, a record that no laboratory on Earth created and that no collision has yet erased. That body and its companion drift on, past 1 year, past 1,000 years, past 1,000,000 years, the same slow orbit repeated with the slow patience of gravity, which does not hurry and does not forget. The sun it orbits is smaller there than it is in the night sky above any earthbound observer. It gives enough light to cast a shadow, very faint on the surface of whatever faces it. The sky around it is not empty. Across the vast expanse of the belt, separated by distances measured in hundreds of millions of kilometers, other bodies trace their own slow paths. Each of them carries its own record. Each carries the same dark reddish surface chemistry, built up by the same radiation, acting on the same simple ices, over the same span of deep time. Each moves in an orbit that encodes the history of the forces that shaped the outer solar system in the first tens of millions of years after the sun ignited. To read those orbits is to read a history that nothing else preserves so clearly, not the moon's battered surface, not the asteroids, not the gas giants themselves, whose fluid interiors have erased whatever internal record they might have held. The Kuiper Belt kept its record in ice and gravity, in the shapes of orbits and the distributions of orbital elements, because the conditions there were cold enough and quiet enough to preserve it across the full span of the solar system's age. The work of reading that record is patient and slow, as befits its subject. Each new telescope survey adds objects to the catalog. Each new object adds its orbital parameters to the statistical distribution from which models are tested and refined. A small team at a high-altitude observatory measures the position of a faint-moving object across 3 or 4 nights of observation, calculating the arc of its orbit from the small shift in position against the background stars. The orbit will need to be refined over years of additional observation before it is known precisely. Many objects discovered in one survey season are lost before enough data have been collected to fix their orbits, found only as short arcs in old image archives, their trajectories uncertain. The work is meticulous and cumulative, and it produces no single dramatic discovery, but rather an ever denser and ever more precise picture of a structure 4 billion years old, assembled piece by piece from points of light that move almost imperceptibly against the stars. This is how the outer solar system is known, not by visiting, which takes years even for the fastest spacecraft, but by watching, by measuring, by accumulating the statistical weight of thousands of observations into a structure that only becomes visible in aggregate. The spacecraft that have reached the outer solar system carry, each of them, a kind of testimony. New Horizons passed through the Kuiper Belt on its way outward, its instruments recording the faint interplanetary environment. The density of dust and the flux of energetic particles in a region no previous spacecraft had traveled. It found the belt quieter than expected, the dust density lower, the particle environment somewhat different from what models had predicted. These measurements will be useful when future scientists model the environment that the early outer solar system objects formed in, or the environment that any future mission would travel through. Pioneer 10 and Pioneer 11, launched in the early 1970s and long since silent, passed through the outer solar system and continued into the interstellar space beyond. They are no longer transmitting, but for the decades they did, they returned measurements of the particle and field environment at distances where no instrument had been before. Voyager 1 and Voyager 2, both now in interstellar space, passed through the outer solar system and continue to return data from the boundary where the sun's influence gives way to the broader interstellar medium. These 4 spacecraft are the only human-made objects beyond the orbit of Neptune. Their trajectories, precisely calculated and precisely measured over decades, have themselves become data. The tiny discrepancies in Pioneer's drift, initially puzzling and later explained by the gentle push of heat radiating from the spacecraft body, taught physicists something about the precision of orbital mechanics at those distances. Every measurement the outer solar system returns is used. The Rubin Observatory, when it reaches its full operational capability, will begin returning new objects at a rate that no previous survey has approached. A new trans-Neptunian object will not be a notable event. They will arrive in large numbers, each one added to the catalog, its orbital parameters recorded and eventually refined. In aggregate, they will fill out the statistical picture of every orbital population, the Plutonos and other resonant groups, the hot and cold classical belts, the scattered disk, the extreme objects in the extended scattered disk, with perihelia far beyond Neptune's reach, where the current sample of known trans-Neptunian objects is too small to distinguish clearly between competing models of Neptune's migration. The Rubin sample will be large enough to make those distinctions. Where the orbital clustering of extreme objects currently rests on a sample too small to rule out chance alignment, the Rubin sample will either strengthen the signal or dissolve it. The telescope will not answer all questions. New ones will arrive with the new objects, but the Kuiper Belt's record will be read in greater detail than has been possible since the first trans-Neptunian object was found in 1992 by David Jewett and Jane Liu, scanning images from a telescope on Mauna Kea with a patience and methodical care that their subject drifting in the cold beyond Neptune would not have rushed. There is a quality to the Kuiper Belt that becomes apparent only slowly across the span of a long time spent in its presence. It is not a dynamic or a violent place,